right, so Wednesday we started this handout on inverse functions, okay? And just to yes, and just to remind you, okay, we defined last time, right? Wrote out the definition on the board, definition of a function, and the definition, this thing is wrong, and the definition of a one-to-one function. And we said, okay, that a definition of function is for each value of x, there's exactly only one value of y. And the definition of one-to-one function reverses that and says for each value of y, there is only one value of x. And so given the graph of an equation, you can determine whether that equation meets the definition of a function by whether it passes the vertical line test or not. And so here we have a graph of a cubing function, graph of a quadratic function. Both of them pass the vertical line test, right? So both of those meet the definition of a function. But to pass the definition of a one-to-one function, they have to pass the horizontal line test. You can see the cubing function passes the horizontal line test, but the quadratic function does not. So quadratic functions are not one-to-one functions, right? But the cubing function is. Okay. All right. Then we talked about only one-to-one functions, like the cubing function up here, have an inverse function. And graphically, right, this is the relationship between a one-to-one function and its inverse, right? We have two sets of numbers, x and y. The function f maps each number in the domain x to exactly one value in the set y. And the inverse function goes in reverse order. It maps each value in the set y to one number in the set x. Okay? So if we have, for a function f, if f evaluated at x equals 3 is equal to 5, then it has to be true that the inverse function at 5 is equal to 3. Okay? So that's how inverse functions just reverse the process. Okay. All right. So here, right, it's a very important comment, right, that we just stated verbally. The function f has an inverse function, f inverse, if and only if f is a one-to-one function, right? So the cubing function has an inverse, but the quadratic function does not. Okay. The graph of an inverse function, okay, is a reflection of the graph of the one-to-one function f about the line y equals x in the coordinate plane. So let's demonstrate that with an example on the board. So I provided you a coordinate plane. And here is the graph of a one-to-one function. It passes the horizontal line test. Okay. And this graph crosses the y-axis at the point 0, 1. Right. That's the y-intercept. And this point right here is the point 2, 3. Right, so here's x equals 1, x equals 2, y equals 1, y equals 2, y equals 3. And then this point out here, at x equals minus 3, that has a y coordinate of 1/2. So that's the graph of a one-to-one function, right? This is the graph of y equals f of x. Now its inverse function, you can find a graph of its inverse function by reflecting this graph across the diagonal line, y equals x. Now, given some points on the one-to-one function f of x, we can plot some points on the inverse function just by reversing the coordinates of the points on the one-to-one function. So by switching x and y for each point on f of x, we can graph the inverse function f inverse of x. So the 0.23 is on f of x. So when I switch x and y, I get 0.32. So the 0.3, comma 2 is on the graph of the inverse function, just by switching the x and y coordinates. Okay. Here's 0.01 on f of x. So when I switch the x and y coordinates, I get to 0.10. That's on the graph of the inverse function. And then we have the point minus 3 1/2. So when I switch the x and y coordinates, I get the 0.1/2 minus 3. Spot right here. So by switching the x and y coordinates of the points on the one-to-one function f of x, I can graph the inverse function. And it looks something like that. So by switching the x and y coordinates on f of x, I get the graph of the inverse function, y equals f inverse of x. Remember, this is inverse function notation. This does not mean reciprocal. If I have 2 raised to the minus 1 power, you know that means 1/2. If I have x raised to the minus 1 power, that means 1 over x. That does not, this is just fancy mathematical notation. Minus 1 in the superscript on the f means this is the inverse function of f of x. It has nothing to do with reciprocal. Okay? It's just fancy mathematical notation. Okay? All right. Any questions on that, ladies and gentlemen? All right. So if you flip over to page 2, at the top of page 2, we have some properties of inverse functions. Now I'm going to just refer to those properties on a as needed basis. You can read through those on your own. But in solving example 2, we're going to take advantage of property number 3, which we have already alluded to on the previous page. And what property 3 says, if f of x, or if f of 2, as an example, if f of 2 is equal to 3, then f inverse of 3 is equal to 2, right? Process is reversed with the inverse function, right? So what goes in to f of x comes out of the inverse, and what comes out of the f of x goes into the inverse, right? The process is reversed. So we're going to take advantage of that property in example 2. Given that the function f of x equal to 6 over x cubed plus 9, right, is a one-to-one function. Without finding f inverse, determine the value of f inverse of minus 1/3. Okay. So what this is telling us right here, right? We're going to find f inverse of minus 1/3. There is some value of x in f of x that is equal to minus 1/3. And because f of x is a one-to-one function, f inverse of minus 1/3 is equal to this value of x. Comes out of f of x, goes into the inverse. What goes into f of x, what comes out of the inverse. Okay. So we find the value of x where f of x is equal to minus 1/3, and we'll know what the value of f inverse of minus 1/3 is equal to. Okay. Well, f of x is equal to 6 over x cubed plus 9. So if f of x is equal to minus 1/3, right, set this on the right-hand side, equal to minus 1/3. And I'm going to write minus 1/3 as minus 1 over 3. Okay? Just to remind you, minus 1/3 is equal to negative 1 over 3, which is equal to 1 over negative 3. Right? You can put the minus sign up front in the numerator or in the denominator. Right? They're all the same, that same decimal value. All right. Well, we got a quotient on the left is equal to quotient on the right. I'm sure that you guys learned in high school cross multiplication. So we can cross multiply. And so when we cross multiply, we have x cubed minus 1 times x cubed plus 9 is equal to 18. I actually probably should put the minus sign in the denominator, but we'll keep on this one. And now we divide both sides by negative 1. And we have x cubed plus 9 is equal to negative 18. Right, now we're solving for x, right? You subtract 18 from both sides and you get x cubed, or excuse me, subtract 9 from both sides, you get x cubed is equal to minus 27. What then does cubing? Cube root, right? So we take the cube root of both sides. What's the cube root of 27? Yeah. So cube root of x cubed is x, and cube root of 27 is 3. So f of 3, right, from over here, f of 3 is equal to minus 1/3. So put in 3 in for x, right? F of 3 is equal to minus 1/3. And so f inverse of minus 1/3 is equal to 3. Oops. What did I do wrong? Let's see. So we subtracted 9 from both sides, we got minus 27. Then I had a dyslexic moment. Drop the minus sign. Yeah, so it's the cube root of minus 27. And the cube root of minus 27 is minus 3. And so f of minus 3 is equal to minus 1/3. And so f inverse of minus 1/3 is equal to minus 3. Everybody see how we did that? Okay. And it's all because this relationship f of x is a one-to-one function, so it has the inverse. Okay. All right. In example 3, you're given two functions f of x and g of x, and you have to verify that the functions f and g are inverses of each other. So you might want to add the word are inverses of each other. So to do that, we're going to take advantage of property 5 up here. To verify f inverse is the inverse of f, show that the composite, right, this is the composite of f inverse with f as a function of x, is just equal to x. And then you got to show the composite in the other direction. Composite of f with its inverse as a function of x is equal to x. So we got to do two composites to verify that f of x and g of x are composites of each other, or are the inverses of each other. So f of x is equal to 1 over x minus 4, and g of x is equal to 1 over x minus 4 plus 4. So we got to show that the composite of f with g as a function of x, right? By definition is f of g of x is equal to x. And then we got to do the composite of g with f to show that it's equal to x. So you know how to find the composite of two functions. G of x is the inner function in this case, so we replace g of x with what it's equal to. It's equal to 1 over x plus 4. And to evaluate f at 1 over x plus 4, right, we replace the x at f of x on the right-hand side with 1 over x plus 4. So this is equal to 1 over x plus 4 minus 4 we have 1 over x plus 4 minus 4. Well, 4 minus 4 is 0. So this is 1 over x. So this complex fraction, this is the main fraction bar, right? So when you do division with fractions, you keep the top number, change division to multiplication, flip the second number, right? So key switch flip, you have 1 times x over 1, and x over 1 is just x. So the composite of f with g is a function of x is equal to x. So we're half done, showing that these two functions are inverse functions of each other. Okay. Any questions on this? So next we have the composite of g with f as a function of x. Which is equal to g of f of x. So f of x is the inner function in this case. So we replace x on the right-hand side of g of x with what f of x is equal to, and that's 1 over x minus 4. So we have 1 over x minus 4, right? I'm replacing the x here in the denominator with 1 over x minus 4. And then we add so again we have a complex fraction, right? We have 1 divided by this quotient. Keep, switch, flip, right? So we keep the 1, change division to multiplication, and then flip the bottom fraction, which is x minus 4 over 1. And then we're adding 4 out here. So 1 times anything is anything. So we just have x minus 4 divided by 1, which is x minus 4. So we have x minus 4 plus 4, which is just equal to x. So f and g are indeed inverse functions of each other. Because the composite of f with g is equal to x, and the composite of g with f is equal to x. Any questions on that, ladies and gentlemen? All right, flip over to page 3. We are going to learn how to, given a 1-to-1 function f of x, we're going to learn how to find its inverse. And we're going to have to find the domain and range of both of f of x and its inverse. Okay? So, in so doing, in finding the domain and range of both f of x and its inverse, we're going to take advantage of properties 1 and 2 at the top of page 2. The domain of the inverse function, f inverse, and the range of the 1-to-1 function f of x are the same. And 2, right, you can read it, you can flip the 2 sides of the equal sign. The domain of the 1-to-1 function f of x is equal to the range of f inverse, okay? Or the range of the inverse function is equal to the domain of the 1-to-1 function f of x. So we know how to find the domain of a function. What's difficult sometimes is finding the range. So we can find the domain of the inverse function, and we can find the domain of the 1-to-1 function f, and use those numbers. Those numbers will tell you the range of f of x and the range of the inverse function. That's what properties 1 and 2 do for us. Okay. And we'll take advantage of this on page 3. Okay. And the steps for finding the inverse function, right, are at the top of the page. So we have the 1-to-1 function f of x is equal to 3x over x minus 4. So step number 1 in finding, so right away, we know what the domain is of this 1-to-1 function is, right? The domain, right? There's no square roots. This is a rational function, right? With x in the denominator, right? The denominator can't equal 0. Right? X minus 4 can't equal 0, which means x can't equal 4, right? And so in interval notation, it's minus infinity minus infinity to 4, parentheses, union, parentheses, 4, plus infinity. So where it says domain of f of x, you can write the domain in interval notation. Right? You know what that domain is. Now, we also know, right? So this is, let me rewrite this. This is the domain of f of x, We also at this stage know the range of the inverse function, f inverse of x. From top right, from the property, top page 2, right? The range of f inverse is equal to the domain of f. We know what the domain of f is, right? So the range of f inverse is the same set of numbers. Minus infinity, 4, union, 4, infinity. Okay. The difference is this set of numbers applies to x and f of x. The set of numbers applies to y in the inverse function, right? Because remember, range is the y coordinates in the graph. So this is y can't equal 4 in inequality. Once we find the inverse function, we can calculate its domain, and that'll give us the range of f of x. All right, so let's go through the steps. F of x is equal to 3x over x minus 4. So step number 1 is replace f of x with y. Step number 2 is replace y with x. And on the right hand side, where you see an x, replace it with y. And then once you do that, you got to solve for y. Okay. So we got to isolate y on the left hand side, right? So on the right hand side, and you know what to do after time, just sheer practice, repetition. So the first step is to clear this fraction on the right hand side, right? This is 3y divided by 1 minus 4. Right? Remember, fraction bars like divisions. So to clear this fraction, we're going to multiply both sides by the denominator, y minus 4. So we have x times y minus 4 is equal to 3y over y minus 4 times y minus 4. Now on the left-hand side, now you got to distribute the x inside the parentheses. And you have x times y minus 4 times x. And on the right-hand side, right, you can see the y minus 4's cancel. Right, multiplication does the division. And we're left with 3y on the right-hand side. All right. Now to isolate y on the left-hand side, you need this term involving y on the left-hand side and this minus 4x on the right-hand side, right? So we're going to subtract 3y from both sides. We have xy minus 3y minus 4x is equal to 0. And now we're going to add 4x to both sides, right? To move that term to the right-hand side. We have xy minus 3y is equal to 4x. And now you can see I have these two terms each have y as a common factor, so I can factor out the y. And then y times x minus 3 is equal to 4x, right? So I went from 2 y's down to 1 y just by factoring. Okay. So we factor. And now you divide both sides by x minus 3, and you have y is equal to 4x x minus 3. So we have solved for y. So the fourth step, right, is it says that replace y with f inverse of x, right? Replace y with inverse function notation. So we have f inverse of x is equal to 4x over x minus 3. So that can go into space at the bottom of the page, right? Down here at the bottom, f inverse of x. All right, so now that we know what the inverse function is, we can calculate its domain, right? So the domain of f inverse of x. Can I erase this over here? Everybody's got this? Right, there's no square roots, right? This is a rational function. You just got to be concerned about x's in the denominator. The denominator can't equal 0. So the domain of f inverse is the denominator x minus 3 can't equal 0, or x can't equal 3. That's inequality notation. In interval notation, the domain is minus infinity 3 union 3 to infinity. That's what goes in the blank here. Okay. Well, now that we know the domain of the inverse function, we know what the range of f of x is. Its y values. It's the same set of numbers. But they apply to y, not x. Remember, range is the y coordinates, domain's the x coordinates. So we took advantage of that relationship. Okay. At the top of page 2, right? The domain of f inverse and the range of f are the same set of numbers. Okay? But for the domain applies to x, the range applies to y. Okay? Any questions on that, ladies and gentlemen? Were you pondering a question?
Yeah. So, was the range for f of x negative infinity to 3? Okay.
So this is the range of f of x.
Okay. Now,
It's the same set of numbers as in the domain of the inverse function.
okay.
But for the f of x, it applies to the y coordinates, right? For inverse of f, it applies to the x coordinates. Any other questions? Are you ready to get a jump on the weekend? Let's do it. Okay, I'll see you Monday.